So, welcome everyone. So, let me first introduce myself. My name is Daan Keuper. I'm the head of security research at WAN Security, formerly known as Contestants. I do vulnerability research mainly, and over the years in my career, I've researched tons of stuff. I hacked iPhones, Zoom at the start of the pandemic. I looked at cars. I hacked EV chargers, OT systems, etc. I work for Debian. Debian is a security company located in the Netherlands and in Spain. We exist since 2005. Basically, we are a full-service security provider. We do everything from pen testing, red teaming, to incident response. We have a SOC, governance, etc. But today I want to take you with me in our journey into one of our Pwn2Own endeavors. I'm not sure if everybody here knows Pwn2Own, but Pwn2Own is a competition that is held a couple of times per year, and they invite security researchers to demonstrate 0 days in targets they have selected. I've participated, I think, 5 times in total now, starting with the iPhone. And this edition was about IoT appliances. So the targets were Sonos speakers, printers, routers, NAS systems, etc., where they give you a list of targets. You are free to research those in your own time. Typically, the target list is presented 3 months before the competition. And then on stage, you have to demonstrate that you can compromise a device of theirs using a 0-day vulnerability or multiple 0-day vulnerabilities. After which, you will go into a disclosure room. There you have to tell them everything about the 0 days you have found and you have used. And they will check with the vendor and in their own systems to see if that was actually a true 0-day or not, if the vulnerability you used was already known. For example, because the vendor was previously notified about this vulnerability, but it wasn't yet fixed, or because somebody else in the competition was before you and used the same vulnerabilities, then you get a point reduction, and at the end of the competition, there's a prize award or ceremony with the team with the highest points wins. So this is a bit about the competition. This was in Ireland. It was the IoT edition. We participated with something which is called the SOHO Smashup, which is a special category for Pwn2Own. It means that you first compromise a router from the WAN side, and then you pivot to some device on the local LAN. In our case, this was a NAS. So this is a special kind of category. We participated and were successful in demonstrating our attack chain. And luckily for us, all the vulnerabilities that we have used during this competition were previously unknown. So I've done a lot of talks about a lot of vulnerabilities we disclosed or found earlier, but most of the times I only discuss, like, okay, this was the vulnerability, this was how we exploited it, because typically that already takes an hour to all describe. But now we wanted to do a talk describing not only what the vulnerabilities were that we found, but also how did we find those vulnerabilities, and what kind of stuff did we try but failed in the end. So much more about the research process that we typically follow, in the hope that we inspire other security researchers as well to do similar kind of research. So of course this all our projects start with some recon phase. And for Pwn2Own, that means we look at the target list that is selected for that edition to see which device are we going to target. And things that we look at are, for example, is there any prior research in this category that hopefully can get us a kickstart into that project? Or is there maybe some expected competition. Like if we know that a target is going to be hot, like there is a lot of teams are going to target that specific device, then maybe switch to another device, because the chance that you find a unique vulnerability chain are pretty slim, because other teams are competing with you and they're looking at the same attack surface. We of course make an assessment of the hackability of a target. Like we expect some premium devices are much more secure than some Chinesian devices. So that's also something we take into consideration. We look at how easy it is to get the firmware. Here we made a mistake for the same competition, because we had a third target in mind as well, where we thought, okay, this might be an easy target. We can get the firmware quite easily. Which it was expected out to be very, very hard. There is another talk you can find online on how we combined all kinds of hardware attack surface with some crypto flaws, etc., to eventually get the firmware, but then time was running out and we had no time to actually find any vulnerabilities. And of course, we look at the price and shipping options, because this is a US-based company that organizes these events, meaning that they also target US devices, and sometimes it is difficult to ship those devices to Europe. For example, EV chargers was a separate category in a Pwn2Own edition in Tokyo, where, well, the EV chargers in US are different than in Europe because of the power grids. So shipping those devices to Europe is sometimes also a problem. So this story starts with the TrueNAS Mini X, because this was the first target we selected. This is the device. It is in no means, it's mini. It's quite a big device. It's a NAS file system. I think it's relatively expensive if you look at their competitors. But the reason why we first choose this as a target was because the software that runs on this device is open source. You can just download it. It's called TrueNAS Core. I think they now have a new version with a different name. But for this NAS, it was TrueNAS Core, which you can just spin up in a VM. And this story actually started on a Thursday night. We had no plans to participate in Pwn2Own, but one of my colleagues, he had a Thursday night off, he had nothing to do, so he decided, okay, let's download this VM, see what happens. And boom, within 10 minutes, he found a vulnerability, and we're like, okay, shit, now we have to do something with this, and now we have to build an old chain, etc. So, but this was the reason we chose the TrueNAS. It's very easy, so that you don't even need to buy the device or do anything. You can just install this, run it, do your research. So this is TrueNAS, the operating system. It comes with a web interface. Of course, the first step is look for attack surface. Like, what is the attack surface from an attacker point of view? And by default, basically everything is disabled. You, of course, can enable certain file sharing properties like Samba or NFS or anything else. But by default, everything is disabled. And typically for the competition, they will let it be in its default settings. So they will just boot up the device, and that is the target you have to target, meaning that if you want to make any adjustments to the settings, you first have to go to the competition leader, say, okay, I want to enable Samba shares, which is a pretty reasonable request, of course, for a NAS file system. But yeah, it isn't on by default, so you have to discuss this with the competition leaders. So another thing we did notice, apart from the attack surface, there wasn't much because most of the stuff was disabled. The only thing enabled by default is the web interface, I think. But if you see there on the left lower corner, there is a button called shell that immediately drops you in a shell. Meaning that if you are authenticated on the web interface, you also have a shell on the device. So this also meant that maybe we don't need something that gives us remote code execution, a vulnerability that gets us to that point. If we have another vulnerability that gives us an authentication bypass, allows us to log into the web interface, we're also done, because we can then just use the shell functionality on the website to get code execution. So for the TrueNAS, the thing what we did was we looked at outgoing network connections. And there was something that we noticed, and that was that there was an URL of an outgoing connection over HTTP, which we can man in the middle, to something FreeBSD, something package site, which is a tar archive. And at first we thought, this is FreeBSD default. I've run a FreeBSD system for quite some time. I know this URL, I know this package system. I think this was FreeBSD default. So we ignored it at the time because we were sure that this was signed and checked, whatever. But then we noticed the user agents, Python requests. Ooh, that is strange. That we didn't expect because by default, FreeBSD doesn't use Python. So that gave away that this wasn't actually FreeBSD default. There was something else running here that was connecting to this package system. So diving deeper, we found out that this was something called IO cage. It's something for jail/container management. It is a Python project. It was used by TrueNAS. I think the project was even abandoned. So we decided to do a little source code digging. And we found out that they used the extract all function, where the documentation very clearly states that you should never do this with user-controlled contents, because the contents can contain dot slashes, and you can get path reversal, you can overwrite arbitrary files on disk. So those are very easy vulnerabilities for us to find. That took like 10 minutes or so. So we can overwrite arbitrary files on the file system as root, which is convenient. So which files are we going to overwrite to actually get a shell? Well, time is limited because during the competition you have 3 attempts that can all take a 10-minute maximum, and you have to compromise both devices in that time frame. Since we had no idea what the other vulnerabilities for the router would be, we're like, okay, it must be as short as possible, because the other exploit might take some time to run, for example, to shape the heap or something. So shorter is faster than, or is better than slower. So in the end, we decided to update just the whole database of the web interface, which also contains the user credentials, with the user credentials that we knew, of course, and then we can just log in on the web interface, use the shell functionality. So the whole attack chain is basically spoof the DNS records, inject a malicious tar file, overwrite the user database, log into the web interface, use the shell functionality, and we're done. So this was the first vulnerability we found. But of course, this whole vulnerability chain requires us to have man-in-the-middle capabilities. We need to be able to spoof that DNS record to intercept the tar file. And man-in-the-middle capabilities is something that you typically don't have with targets for Pwn2Own. Hey, you're placed in the same local LAN, but you're not allowed to do man-in-the-middle attacks. Unless you're in the SOHO category. Because in the SOHO category, you first hack a router on the web interface, and then you pivot to something on the local LAN. Well, if you're already on the router, you are, of course, already a man in the middle. So that was our plan. Like, okay, we can use this vulnerability for the competition. It just means that we also need to hack a router. The list of routers is mentioned here. It's Synology, QNAP, MikroTik, Ubiquiti, and a Nest. So we looked through that list. We ordered, I think, the MikroTik and the QNAP. We skipped the Synology because the Synology was already a target 3-4 years in a row. So we're like, okay, I'm guessing I hope that the pool of vulnerabilities was already dried up. The Ubiquiti, I have one at home. I'm sure there are vulnerabilities, but we expected it to be better secure than some of the other targets. Same goes with the Nest, which is of course from Google. So we thought, okay, let's buy the MikroTik and the QNAP. And the rest of the story continues with that QNAP. This is the device. It's it's a router for secure networking experiences. It has 7 unique remotely exploitable vulnerability chains, apparently, because there were 7 chains demonstrated during the competition. It's one of the most expensive routers on the list. It was like 600 euros or so. I'm not sure what else to tell you about the router. It routes packets. It does what it needs to do. So before we ordered the device, the first step was we ordered the device and then we had to wait for its shipment to arrive. So the first step was, okay, can we already obtain the firmware to do some static analysis while we wait for the device to arrive? So the QNAP website gives you a download link to the latest version of the firmware. But if you plot the entropy, you can see that, most of it is encrypted. So we're like, okay, we don't have the password. Maybe we can find it online. Maybe somebody already figured this one out. Well, indeed, there is a Python script that works. You just have to supply it with the password. I think for the QTS, which is a NAS system, the password was QNAP. Turns out for the QHORA, the password is QHORA. I have no idea why you go through the trouble of encrypting the firmware if your password is so simple. Like, what does it gain you? But okay, firmware decrypted, so we could already look at the firmware and start analyzing some binaries in IDA. Once we received the device, we immediately voided the warranty by opening it up. There is a nice labeled debug port on the device, which gives you a shell over UART, because by default it doesn't come with a shell. If you look at the QNAP documentation, they say that SSH is insecure, so they don't offer you that option on your router. Fine, then we just use the debug shell. You can immediately log in with the credentials that you also use for the web interface, so that makes analysis a whole lot easier. So now we have shell on a running system. We can debug binaries, see what's running, what is binding to what port, etc. And we have the firmware that we can load in IDA, etc. So perfect debug setup. So the first thing we did, just as with the TrueNAS, because we already got lucky there, was look at outgoing connections. Like, what kind of connections is the QNAP making to the outside world? Well, there are quite a few. Of course, DHCP, NTP, DNS, but those are all backed by binaries that are well researched and to us didn't come off as easy targets, so we decided to skip those. But there were 2 QNAP managed binaries that also made outgoing connections. The first is Cloud Agent. It makes a whole lot of TLS requests to my QNAP cloud, etc., to get firmware updates, to do remote management, etc. We try to man-in-the-middle those connections by replacing the certificates, because certificate validation is very hard. We found tons of vulnerabilities in certificate validation in other mobile apps, IoT devices, etc. But in this case, it seems to all work out. It didn't accept any of our malicious certificates, so we dropped this as a target. Like, we cannot intercept connections to the QNAP cloud. Another binary was NCSID, which stands for Network Connectivity Service, I don't know, something. Basically what it does is it does an HTTP request to a TXT file somewhere on the QNAP website. And we're like, hey, this is nice. We hacked TrueNAS with some HTTP requests. Maybe we can do the same with the QNAP. That would be nice. We reverse engineered the binary, and what it does, it tries to see if it has network or internet connectivity. It stores the file somewhere in /TMP. The data of the file itself is never processed, whatever. It only looks at the HTTP headers, and it parses the HTTP headers with a regular expression. And basically, it checks for the 200 OK status codes, and it checks if the content length is 5 or some other magical value. And if any of those 2 conditions is true, then it decides that it has internet connectivity. No parsing of the data is done, no HTTP header parsing, it's just a regular expression over the raw data. So we dropped that as a target as well. So then we decided, okay, let's look on the listening services. Like maybe there's something we can connect to find vulnerabilities. So there are some TCP services listening on this device, but they're all blocked by the default firewall. And turning off the firewall, that is obviously a bit lame and also not allowed by the competition rules. So they were out of the question. There were also 2 UDP services that were listening on the WAN side. The first is Sharon, which is a IPsec authentication provider, also well known. So we also didn't look further into Sharon. But there is also one other UDP service, which is called Q1WMD. Not sure where it stands for. I'm not even sure what its purpose is. But you can connect to it, and it expects some JSON blob with a sender, a receiver, and a WAN something. And if those fields are present, it will give you some debug output, like what is the current memory usage and the current CPU usage. I have no idea why this listens on the WAN side to all incoming connections. I have no idea, but it is there. You can speak to it. It also does some validation on the fields, like the sender should be a number, and if we supply it with a string, it aborts because some assertion fails. So, okay, we can make it crash, but yeah, that doesn't give us code execution. We tried to reverse engineer it a bit more to see, does it actually use any of the fields for some further processing that we can find vulnerabilities in? Turns out it doesn't. It only checks if those fields are there, then it checks if the types are correct or what it expects, and if so, it prints some debug statements, and then it bails out. The data isn't processed in any other form. Of course, we could have looked at the JSON parser itself to see if we can find some vulnerability in the JSON parser, but we first decided to look at other attack surfaces because that might be easier than exploiting this. So, what other attack surface can we actually get? Like we have, we looked at the outgoing connection and we looked at the listening services. What other attack surface do we have? Well, we can of course try to see if the attack surface changes if we also hand out an IPv6 address. We could see if there's any traffic manipulation going on from traffic that goes from the WAN side to the client side. For example, for deep packet inspection or whatnot. It might be that such a functionality is there and we can find some vulnerabilities there. We can of course try various state changes, like only handing out IPv4, blocking certain traffic, dropping traffic midway, try to only intercept certain SSL connections while leaving the other ones untouched. Everything that might push this box into a different state that we haven't seen before. Let's see if we can force a state change that will give us new attack surface. And then just observe the results and rinse and repeat until we have some attack surface that sounds promising. So this is a lot of work and also very error prone. For example, some of the other teams that were competing with this router noticed that in certain situations, the whole web interface was accessible over IPv6. Where for us, I don't know, I have the port scan results. For us, it was closed. I have no idea what state change they used to actually get it to open. But this is very error prone. Sometimes it works, sometimes it doesn't, sometimes it depends on environmental factors, etc. So this is not always clear. So looking more closely at the device, we saw one other listening service, which was listening on a strange IP address, 198.19.0.0. It was a TCP service. We said, okay, what is this service and what is this IP address? It turned out that it belonged to some tunnel interface that the device had by default. And we're like, okay, but what if we supply the router with this IP address over DHCP? What if we give the router this IP address on the WAN side? What will then happen? Well, it turns out that then you suddenly can connect to this service on the WAN port as well. Okay, cool. So now we have more attack surface to play with. Let's see what this service actually does. Well, after some more reverse engineering, we came to the conclusion that it's an implementation of this RFC. It's called the benchmarking methodology for network interconnected devices. I think it's used to monitor traffic throughput. So it has a port, you can send it traffic, and it will ignore the traffic completely. It will just look at what is the throughput on this port to do some benchmarking. We found the function that handles this traffic, and it receives data in a loop, in a buffer, but the contents of the buffer is just completely ignored. There's no reference to the buffer being, that data being parsed, whatever. It's just in a while loop, receiving in the buffer, omitting any data that was priorly written into that buffer. So we already looked at quite a bit of attack surface, like UDP services, external connections, internal connections, etc. But we didn't have any vulnerabilities yet, or any attack surface that sounded promising at this point. So we decided to look at the outgoing connections one more time, specifically to the DNS connections that were outgoing. This is a list. Anybody sees anything of interest? We missed it the first couple of times. I'm sure you will miss it as well. It is here. It does a DNS request for the quadruple A record for localhost, which is a bit odd. Like, why would it send out a DNS request for a localhost? Only quadruple record, by the way, not for the A record. We had no idea why, but we decided, let's give it our IP address. Let's tell him that localhost is at our place today, and let's see what happens. So we responded to this DNS query with an IPv6 address of ourselves, just to see what happened. And it turns out that we then get 2 incoming connections on 2 different ports that we earlier didn't see. The first is a plain HTTP connection, and the second is something which is called gRPC, which is a inter-process communication protocol by Google. Since the second one contains binary and we have to set up a whole gRPC endpoint and whatnot, we decided let's first start with the HTTP one, because that is much easier to build a mock-up for. As you can see, it tries to reach some API for scanned devices. So what is this binary actually expecting? So the binary issuing this request is called DM agent. And it tries to connect to RapidsD, which is some kind of database, I'm not 100% sure. And to access this database, it uses curl with localhost. And it turned out that the etc host file on this device has a record for localhost for an IPv4 address, but it doesn't have one for IPv6. And curl then, it tries to use etc host, and if that doesn't work, it does a DNS request for the quadruple record. Okay, so it expects a JSON response with a list of all the connected devices. And at first glance, this looks pretty promising. It looks pretty exploitable. This is how the JSON normally looks like. And we got this from by just intercepting the traffic without messing with DNS. It has the OS of all the clients and the model and the name and the MAC address and whatnot. And this is how that data is parsed. It uses a raw string copy to move that data into some internal struct. Of course, there is no length check here, so we can override arbitrary memory. Like, if we supply it with data with a OS name or whatever of, I think that the default size or the buffer size here is 64 bytes or so. If we supply it with something longer, we will override memory. So we're like, hey, this is interesting. It copies data to a heap struct. It copies an array of objects. Like, there are multiple clients, so we can trigger that string copy multiple times. And we notice that the MAC address is actually used in a call to Popen. So we can just, in that MAC address, by theory, we can just insert arbitrary system commands in there, and the device will run it at some point. There was some downside to this. The first one is there is a sleep before this happens of 5 minutes. So it will parse the data, then it will sleep for 5 minutes, and then it will do the call to Popen. And we're on a clock here. We only have 10 minutes, so waiting 5 minutes where we don't know if the attack succeeded or not, it's not ideal, but okay, we'll work with that one. More problematic is that the format of nothing was checked. The only format that was checked was of the MAC address. It has to have this format. It can then have arbitrary characters, but it must have the colons on after every 2 bytes. So we cannot inject arbitrary system commands in here. So we thought, okay, but maybe we can use a string copy of another field to override the MAC address. So it will first be forced into a specific format, but if we then override that MAC address with the string copy, we might be able to inject an arbitrary system command. We cannot do that directly because the MAC address is at the very top of the struct, so all the string copies will happen after the MAC address. So in memory layout, we will override everything after the MAC address. So we have to do some trickery here to make that work. This is how that will look in theory. Like, this is the heap, and it has different chunks where it can store data. So it will first store the information of device number 1 with the MAC address and the operating system and the vendor, etc. We can overflow any of those fields because it's a string copy, so we determine the size. So if we give it a very long vendor name, it will override in the memory block adjacent to where the current information is stored. But currently there's nothing there. And then it will allocate memory for the second device, and that will basically override what we have already written there. So the MAC address will then be stored there, and the new device name and the new device vendor, etc. So yeah, we cannot directly override the MAC address. So typically in such a situation, what you do is what we call heap shaping. We try to force the heap in a certain state that we can override that data. For example, if the heap is already populated with some random data, we don't really care about this one, then a new allocation is made, which will contain the device info for the first device. What if, after that information is stored, we can somehow make the device free the block before this allocation? Then the new allocation, so the new device it will parse, will be allocated before the first device. And if we now trigger the buffer overflow, it will override the MAC address. And then we can write whatever we want. So this is how this works in theory. Works beautifully. In practice, this, of course, can be very tricky. We spent quite some time for this to work. First, something else. Some fields needed to be 0 for this to work. There are some details I haven't mentioned here, but there are some fields in this whole struct that need to be 0, and we cannot really write 0 or null bytes because we're in a string copy, and a string copy stops whenever it encounters a null byte. So we thought maybe we can use the fact that we have multiple string copies in a row to write multiple zeros as well. So how that works is, suppose we, with the first buffer overflow, we overwrite some data. It will always be null terminated, so the null is at the end. But suppose we also want the blue or the green characters also to contain a null. What we can do then, oh, the colors are different, is use a second string copy to override everything to the other byte that we want to have a 0 in. And then use the last string copy to write a null byte to the final place. And now we have something that has a null byte at the exact locations that we want to have a null byte in. So this all looked promising. We're like, okay, we're going to get this to work. But it turned out to be much harder than we anticipated for a couple of reasons. The first, creating that free block before allocating the first device turned out to be tricky. We tried to see if we could do something with HTTP headers. Maybe if we send an HTTP header twice, it would deallocate the first header. We tried to do it with JSON fields, like what if we specify a JSON field twice, maybe it will deallocate the first one when it starts to parse the second occurrence. Didn't really work reliably. Then we thought, okay, then we also found out that we needed to write more 0 bytes than we had string copies. So we also had a problem there. So this all turned out to be very tricky. And the last thing that pushed us over the edge was this is all very flaky. Like that heap needs to be in a very consistent state for this attack to work. Because if the heap is in a different state than we anticipate, then the whole attack doesn't work. And that is, yeah, you can try to push it into that state with a lot of hard work, but every update that QNAP pushes might change that heap status in a way that we cannot anticipate, and then we have to start over. And QNAP was pushing a lot of patches. Like these were the patches in the weeks before the competition. And all the release notes just mentioned some security fixes, etc. And they knew that this competition was coming, and they were patching stuff at the last moment to see if they can fix some bugs at the last moment. But any of them could, of course, change the state of the heap that we were trying to push in a certain state. So at the end, we decided, okay, this vulnerability is not worth it. We can always work on this vulnerability a bit more. But there was, of course, another incoming connection, namely that gRPC service. We're like, okay, let's look at that. So the gRPC service is handled by a gRPC handler, and it tries to connect to Cloud Agent for some messages. There are multiple different messages that are being exchanged between those services. But one of those calls expected some JSON, which they called or referred to as a site info. Not exactly sure what it is, but it expected some JSON. And we, of course, since we can impersonate Cloud Agent in this case, we can send it arbitrary JSON. So this is the normal JSON file that it expects, the site info. It has a lot of fields. Or like, we can always just try to see what happens if we just give it a shell command in every field. Like, maybe this works. Who knows? Turns out it doesn't, unfortunately. But well, it was a good educated guess. Would saved us a lot of time. So then we actually had to look for, okay, how does this actually work? Turns out that it's rather complicated. Like, it writes the JSON to disk, then another daemon will pick that up. That will kickstart a Python process, that will compile Python process, so that we don't have the raw source code. It is compiled. Look for a modification. Based on the modifications, it will send out RPC messages to other services, and that will act on the data. So this turns to be a hot mess. This is a schematic view of how that works. So we have Cloud Agent that receives a gRPC request from NM gRPC handler, expects some JSON, then the binary will drop that JSON as site.json on disk. Then a binary called DAS will get a notification, hey, this file has been changed. That will kickstart a Python process. That will look for modifications, and that will then send out RPC messages to other services, such as RMGMTD. I have no idea what it means. So this is how this would work normally. But of course, we are here. We can mess with anything we want. This looks very cool, but at this point, this is more realistic. I have no idea what we're doing. We're just messing with fields to see what happens, to see if we can change anything that would give us code execution. So we decided to reverse engineer that Python script a bit more, because that is where all the data is being parsed. It is compiled Python, so you can decompile it, but you don't have any comments. It doesn't read very nice. The whole parsing of this file is very, very complex. There are all kinds of if and else conditions on that whole site.json. And we only had a snippet of it. Like, there can be much more complicated sites.jsons with much more fields. And they're all connected to each other, whatnot. And if the stars align, it will send out RPC messages to other services. And at some point, like, we started auditing this, and we're like, I have no idea how this works. This is very complex. What if we make the assumption that there will be a vulnerability in one of these services that it connects to or sends an IPC message to, and just leave this Python mess for what it is? So what we thought was, okay, let's take a single IPC call at random and see if we can create a site.json that will trigger this IPC request. And we picked one at random at line 1518. We're like, okay, let's see if we can trigger this one and build a site.json around this one. This is more easier than try to understand the whole script parsing in its entirety. So we just decided to pick one at random, see if we can make that work, and then use strace to see where that data is being sent to and how that is parsed, to see if we can find an easy vulnerability. Luck was on our side because we found the vulnerability on the first try. Like, we picked one service at random, used strace on the receiving binary to see what it did. It turns out that if you have a site info with multiple sites and whatnot, and you have a WAN address 6 field, and you include some shell script in there, it will happily run that in a shell for you, giving you code execution. So now we have code execution on the router, and we can pivot from there to the NAS. We have a full chain. The only problem here was that for the TrueNAS, we only tried this in a VM because we didn't have the actual device. Because we were like, we can buy the device if we also have a vulnerability in the router. And if we don't have a vulnerability in the router, then it's no point in buying the actual NAS, because then we won't participate. So this was a few weeks before the competition. And we're like, okay, we're done. Let's buy that NAS to see if this vulnerability we found also actually applies here. And then it turned out that it was out of stock everywhere. So we couldn't actually validate if this vulnerability was there. So, but we were pretty confident. So we booked ticket to Ireland. We're like, okay, just gonna try it. Pretty sure it will work. Without actually ever seeing the device. So the first time we actually saw the device was during the competition, and it was way larger than we anticipated. Like, it's a huge box, but okay. So the competition, how the competition works is if there are multiple entries for a single target, there will be a random drawing. So all the names of the teams will go in a hat. They will randomly draw randomly draw names, and that will be the order that you have to compete in. Meaning, you want to be lucky in that drawing, because everybody looked at the same attack surface. Chances that you have collisions are pretty high. So if you are 7th in line, you're bit out of luck, because 6 teams before you already tried to hack the exact same device. Chances that they have the same vulnerabilities are very, very high, of course. Turned out that luck wasn't on our side. We were 7th and last in this whole chain. So we're like, okay, these were 2 relatively easy bugs, especially on the TrueNAS. Very easy. Everybody could have found this in 10 minutes. Even the QNAP, like if you notice that there is a connection going to an outgoing connection for a local host or DNS request, pretty sure that you will be able to find this vulnerability. So we're like, okay, we're going to have a collision for sure. These were the competitors before us. There were some collisions, but also some successes. And some of the collisions were not in the QNAP, but in the device after the QNAP. We got lucky. All the vulnerabilities we had were unknown to the vendor. Yeah, we're pretty fond with that one. As a last thing, I want to show you the video of the exploit in action. On the left-hand side, we're first going to hack the router, and then on the right-hand side, we're going to pivot to the TrueNAS. Let's see. So we run the exploit. We wait until we get a request from the router. Then we wait for a quadruple A request to localhost. Then we wait for incoming connections until we get that gRPC connection. And then we have to wait until the right gRPC message comes along. And then we have a shell as root. All right, cool. Then we can now pivot to the TrueNAS. Basically, we just wait for that request to the FreeBSD package management, serve it with some malicious file, and then we can directly log in through the router to the web interface. All right. Thank you for listening. I'm sure if you have any questions, I'd be more than happy to answer them. Thanks.